course from chemistry, and me and Oyanab also credited that course.
Okay,
Yes,
so
sir.
all of you are there. That is number one. Number two is that did you do, all of you have done a quantum mechanics course in the second year, right? Either chemistry or physics.
Yes, sir.
Either chemistry or physics. So, has any of you done both the courses, chemistry, quantum mechanics, and physics, quantum chemistry, quantum mechanics, in second year?
Yes, sir.
Yes, sir. We
In,
have done second year.
yeah, both the courses.
Yes, sir.
Yes.
Oh, okay. So that then you should have a good knowledge of the basics because you have done two courses. Okay, that's good. So, yeah, I mean, this course will be taught by me and Dr. Sangita Sen, who is also here. She, of course, has joined in the last semester as a new faculty, and she taught with me the second year course last semester. Okay, our basic quantum mechanics. So she will be teaching your batch first time. I have obviously taught you in some point of time group theory as well as in the second year course when you are there, right? Yeah, second year course I must have taught you, right?
Yes, sir.
Yes. So along with Moshumi, madam. So yeah, but this time I talked to Sangita madam. So anyway, so I think all of you have a basic grounding on quantum mechanics. So what we will do today being the first class, first we'll discuss this syllabus, but the syllabus will not come necessarily in the order in which it will be written. I think we will try to rationalize depending on your what you know. And so the basic syllabus, if I remember, Sangita, you can correct me, is of course there will be discussion on certain approximate methods like perturbation theory, including WKB, variation method, and then basically this course will focus on the many particle problems, many electron problems. Not necessarily they will be dealt by what are called many body methods, but they will certainly utilize many electron problems. So many electron problems, as I will show you, are extremely difficult to solve, and exact solutions are just not possible for interacting problems. So that is where there are lots of approximations which are developed, and that will be the basic idea of this course, which will run you through the simple theories like Hartree-Fock to the perturbative and variational methods of different types. Hartree-Fock itself we will see is a variational method, but there will be other methods which include what Hartree-Fock does not include, and that is called electron correlation. So we will do configuration interaction, maybe even multi-configuration Hartree-Fock, then perturbation theories of different kind, in particular Euler and Placet-Versen, and then at the end maybe a little bit of the couple cluster, which is a very standard method and very accurate method in quantum chemistry today. And if time permits, we'll give an overview of a completely different class of methods that is called the density functional theory. So DFT, as all of you know, because that's a very popular method, so I will not leave it out. So this is my plan. Sangeeta, I will request Sangita to add if something I missed out from the syllabus.
No, not really. I think we have covered
Yeah, all right.
most of the things.
So that being the case, let me first say that there will be a lot of reference books that we will give, but one of the books that I will follow primarily, at least in the beginning and most of the course, is a book by Attila Szabo and Neil Oslund. I will write it down in the screen. I think the book is called Advanced Quantum Chemistry or Modern Quantum Chemistry. Do you remember, Sangita? Is it called Advanced Quantum Chemistry or Modern Quantum Chemistry? I have forgotten. But something like that, either Advanced or Modern Quantum Chemistry by Szabo.
Modern.
Yeah, by Szabo and Oslund. All right. So I think we will mostly stick to that reference book. Yeah, mostly we'll stick to that reference book, and then on and off we'll give you some references. I will also give you a material for video, which is there is no copyright, so that's the reason I can give you. I had conducted a very similar course, though the flow will not be exactly same as the one I took. A very similar course at IIT Bombay in 2017, exactly January session. So 4 years before. 4 years before, I had taken a similar course. And that is actually available in a site of IIT Bombay, which is called CDeep. I will give you entire reference. It is basically a distance education program of IIT Bombay. So they do video, but the only issue there is that you cannot download. You have to create a login, and then you can view those videos from lecture 1 onwards, though the flow of this course will not be exactly same. So that is only for a reference. You can see many of the lectures will be identical. So you can see there is a large amount of reviews of basic quantum mechanics there, which you may not be able to do that. I think I had about 41 lectures there. We will have similar lectures. All right, so I will give you that reference as well. I don't know if any of you have already seen this video. CH560 on the CDIP site. If not, I will give you that reference. The next point that I would like to also mention, that this course, although we have two teachers, Sangita ma'am and myself, the course will be taken, I think, about 70% by Sangita ma'am and 30% by me. Is that fair enough? Should I announce that, Sangita?
Yeah, it's okay.
Okay. I mean, that is for various reasons. Last year, I took this course alone, which means I took almost 100%. Ashwini Tiwari only took 2 lectures on basis set, but I otherwise took almost all the lectures. So I did 100%. This time, of course, Sangita ma'am is there, and she's also very capable, like Ashwini Tiwari and others, very capable to take this course. And I think she's new. It's a good for her also that, in the future she can take up these courses. As you know, that I'm no longer the future, okay? I'm just the present at this point of time, right? So I think we have decided in the way that, but this is a decision between us, and this can change. I must also say, this may change any point of time. It is not a decision by the academic section. The academic section has put both of us as the co-instructors. So depending on the situation, we can change. I can take more classes. I can take less classes, also depending on what you want, and so on and so forth. Okay. So I think I just thought I will mention that. But at this point of time, that is the decision that we have taken. All right. So with that, I will try to share the screen. And this course is named as what? CH4211, Sangita?
Yes, 4211.
Okay. So what I'm doing, of course, is that I don't know, the Sangita, what is your plan? How you are going to teach?
Okay, now I have got an
Hello?
iPad, and I will also teach like you are doing now. So it will be
Okay,
the same.
great.
Yeah.
So both of us will be basically teaching through the pad, so that we have as much classroom feeling as possible. So that we will not just give you PowerPoint presentations and see and discuss. There are many people who are doing that. They're showing the slides beforehand, so that you see the video, and then they discuss. In this particular case, it is particularly not exciting because one video of my own lectures are already available at IIT Bombay site, which can be seen by anybody. There is no copyright violation. So it's a distance education, and they promote that. So already that is available. So those who can go and see, and these videos will also be recorded. So can we start the recording for this? Sangita, is it being recorded? Yeah.
Yes, sir. It's recorded.
Yes.
So this will be also recorded, plus the slides will be shared to you through the Wheeler. So there are multiple options of learning. Okay. So you don't have to bother. The course is for very smaller number of people. So it is very exciting in some sense. I have always enjoyed taking this particular course. And personally, it is one of my favorite courses. Okay. It's just that I don't want to take too many classes now. So that is the reason I'm taking 30% as of current decision. All right. So this is the CH4211. It is basically advanced quantum chemistry, just as the book of Szabo and Oslum is mentioned. So one of the reference books, so let me write down this first before we start, is the screen seen, right?
Yes, sir.
Yes.
Okay. And the pen writing is also deep enough that you
Yes,
can
sir.
see. Yeah. So it is by Attila Szabo, A. Szabo, and Neil Oslund, Neil S. Oslund. I have forgotten the publisher. Do you remember, Sangita, what the publisher? But anyway, you can see this
No.
in
This
the Google.
book is available as PDF online as well
Yeah.
as in our own library in IISER. So that,
Okay, great,
yeah.
great. So it is available online as well as our library.
Yeah.
So this is a master book actually. Although we will refer you to other books as and when it comes. All right. Then I wanted to point to my video of IIT Bombay. So the site in which you have to go is cdeep dot iitb dot ac dot in. So that's the site that you have to first log in. I'm not sure if you have to put www dot or not, but just check that. It doesn't matter. So once you go there, you will actually have to create a login. Once you create a login, you will see lots of courses which have been recorded. So you have to probably come to chemistry and then search for the course of CH560 in 2016-17 session. This is actually semester 2, so it was 17 January 2016-17 session, and you have to enroll. I think there is some procedure of enrolling. Even though you have a login, you have to. So every course is not available unless you enroll. So some kind of a registration for this particular course you have to do. Once you do that, after that the videos will be seen from the lecture 1, lecture 2. So you have to just go through each of them. Obviously, in certain video there will be some small errors. I have not gone and checked. Unfortunately, I did some editing, but the editing was not perfect. So there may be one or two small errors. If you find, you can let me know also. So while we teach, anyway, I'll correct that. So I hope you have noted it down, cdp.iitb.ac.in. So you will see this with my name as instructor. So you have to log in there. And that is basically a similar course, although the flow may not be exactly same, because I myself have not seen before I started this class how I did. And since, of course, we have Sangita madam who will teach a larger portion of the course, the flow will be obviously different. So this can only be used as a reference material, and we can have a discussion at that point of time. Okay. So I think these are some of the references that I can share with you. Is there any question that you would like to ask? I will come back to the evaluation a little bit later, but is there any question that you would like to ask on the course content? We already said the course content. So course content would be basically the many electron problems with focus in chemistry. So basically this is what is called the electronic structure and not the dynamics, I must say that. Because the dynamics, I suppose there is a separate course which Dr. Ashwini Tiwari takes. So this will not be on the dynamics. We will not also talk of group theory, but the references will be there. So this will be mostly to solve electronic structure theory, which means essentially to solve the Schrodinger equation for interacting problems. So how do you do that? That is going to be the course. So it's a very straight electronic structure course. You have any questions, any of you, before I proceed further? Is it all right? Can I proceed now?
Yes, sir.
Yeah. So next is evaluation. Yeah. So there was a discussion about a mid-semester examination. I think there will be a mid-sem exam. I will let Sangita madam first talk about it, how the syllabus, how the evaluations will be done. There was a discussion whether the mid-sem exam should be proctored or not. We had an option to opt out, and our number was very small. Because our number was small, so we have opted out. Is that right, Sangita?
Yes,
Hello?
we have opted
Yes.
out of the proctored examination
Proctored.
because I thought it would be too much hassle for the
Yeah.
students to do
Yeah.
all the.
So now can you tell them, I will also write it down here, how do you want to break it up in terms of internal test assignment, mid-sem exam, end-sem exam, etc.
So what? One thing I wanted was if really below 10 in yeah, we can give them all a very short project, like all different. So then there is no scope.
Hello? Hello? Yeah. So, what did you say?
Yeah. So one thing I was thinking is if it's okay, like we can have all different question. Like one maybe some sort of small project, not very big.
No, that is for
Uh,
the end-sem exam or mid-sem exam?
I don't know. We can do it either way.
Okay, but no, but
Mid-sem,
what is the...
like the conventional one, so we can do
No,
it
no,
for mid.
I agree that either way you can do. I'm not asking about the question. What is the percentage marks for mid-sem, end-sem, intern?
Percentage mark for okay, the split up.
Ha.
We can have and I don't know what the students would like. Maybe like 30, 30, 40 is always reasonable.
So end-sem is 40.
NSEM is 40, mid-SEM 30, and
So
internal
I will internal of all kinds, 30.
of
So
all kinds
class,
together
yeah,
30.
class stress assignment. So
Yeah.
and you are saying that we may give different questions to each one of you, each one of the candidates in either mid-sem or end-sem. That will decide later.
Yeah. Maybe we can have like one set of common and one set different.
Yeah,
If
so
it's
that's
like
okay.
really
That's a different matter. But
Hmm.
is this breakup acceptable to all of you? Or do you want this to be
Maybe we
reduced?
can think about it and come back. That's all.
So in some should can be a 30 or maybe 35, 30, 30 and
Okay.
30, and then 10 for like attendance either, or maybe for some interactive session, or ma'am was saying some project work. So
Yeah, but the project work was part of the questions. Part of these questions. So are you
okay,
suggesting
sir.
this that mid-sem and end-sem should be same?
I was saying 30, 30 mid-sem and 30 and in-sem 30.
Yeah, so I've written down in the last column. See this.
Yes, sir.
Is that okay, Sangita?
Yes, that is fine. That is fine with me.
Is there any directive from the academic section? Hello?
Yeah.
Is there any directive from the academic section? How we should split? No.
No. We don't have any
Okay, all right.
directive yet.
All right. So then we'll come back to the nature of the questions, multiple choice, project, as Madam said, or subjective. As we go ahead, we'll worry about it. But as of now, I just thought I will give you a brief. But this breakup is totally flexible. As we go along, we can change it. Okay, we
Okay,
can
sir.
change the breakup, and the exams will not be proctored. Okay, but at the same time, I trust that we will not copy. That's of course needless to say, and that is the
Yes,
reason
sir.
we have said let's trust the students and not have a proctored exam. So I hope you will keep this in mind. All right.
Yes, sir.
Okay, great. So I will now actually start on the class. All right. So I think since all of you have done quantum mechanics, I just have to revise the basic postulates of the quantum mechanics. So one of the very important part of the postulate is the first postulate, that for every state of a system, not only there is a system, but every system has many states. So for every state of a system, there exists a wave function psi. That is very important. So that is where the quantum mechanics starts. And the departure is when I actually give an interpretation to psi, saying that the mod psi square is the probability density. So this is where there is a departure from the classical mechanics, that we say that we don't know where the particles are, but I can only talk of the probability density. So this is basically a kind of position coordinates. So these are some kind of position coordinate. Let me write this as an x. You will later see that this will also involve another set of coordinates called the spin as we go ahead. But this mod psi square is the probability density of the particles being at x. And x is a composite index. It may not be one particle. it may be two particles, then there are x1, x2, and so on. Okay. So, and I'm not writing r because this also will include spin later. So there are spin coordinates and the space coordinates. So a particle, probability of a particle being at a particular point with a particular spin. So that is how this x will differ. So this is something that you already know. And then we had, for every dynamical observable, I'll very quickly run through that in 5-10 minutes. For every dynamical observable, there exists an operator, a quantum mechanical operator. And of course, since these are observables, these operators are Hermitian, which have lots of nice properties, that the operators are uh, operator eigenvalues are always real. You can construct an orthonormal set of eigenfunctions for the Hermitian operator. You can construct, even if they seem at the beginning not to be orthogonal, by a linear combination, you can always construct. And this happens only in the degenerate space. For the non-degenerate eigenvalues, they are automatically orthonormal, but for degenerate, they are not. And just to tell you the Hermitian operator, let's say a basic relation of the Hermitian operator, that a matrix element of course, all of you are already familiar with the Dirac notation, right? Hello?
Yes, sir.
So I'm not going to write the integral over entire space and all that. So the conjugate of this number is nothing but phi a psi. So that is the feature of the Hermitian operator. Okay. And if it is a normal operator, what would happen is that this side there will be adjoint of an operator. But since the Hermitian operator is self-adjoint, this is the definition of a Hermitian operator. And from here, you can derive both the theorems, that the eigenvalues are real, the eigenfunctions can be constructed to be orthonormal. Is that okay? So this is a very important postulate. Then further we said that in a position representation, these operators can be written, any operator can be written as a function of position and momentum. And the momentum as an operator can be replaced by h cross over I derivative with respect to x in the position representation. And x is simply replaced by multiplicative x. So you just multiply. So that is the way that you construct. So you start from a classical variable which is known, and then you construct the position and the momentum operators. With this, you replace and construct the operator form of the A. So that is a very important point. The third part of the postulate, the next postulate, I mean, it depends on how you tell the postulates, but the next postulate I would say is that in general, for a measurement, there is an interpretation here which was given in the Copenhagen, that every measurement always yields eigenvalues of the operator, and they are of course real. So even if the state of the system is not an eigenfunction, you always get an eigenvalue. I hope that you remember. So it's of course very important to know that the state may not be an eigenfunction of the operator A, but the result that you will get are always eigenvalues. But if the state is not an eigenfunction, then what will happen is that the result that you will get will not be necessarily same. You will get different eigenvalues. So for example, if I have, these are the eigenvalue equation of the operator A, for a given state psi, which is different from any phi I, you will get as a result of measurement a scatter of AI. So not necessarily a particular AI, but a scatter of AI with a probability which can be predicted. And that is important. So it is not totally madness. It is not totally random, with a probability that can be predicted. So how do you predict the probability? A particular AI has a corresponding phi I as an eigenfunction. So if you take this value of phi I with psi, then the modular square of that is the probability of getting AI. So basically, this quantity is the combination coefficient of psi if I expand in phi I. So that's a linear combination in terms of any eigenfunctions, because they form a complete orthonormal set. And because they're orthonormal, it can be shown that those coefficients are nothing but phi I psi, and the square of those coefficient, or modular square of this coefficient, is the probability of getting a particular value AI. For a measurement capital A, and the state is psi, which is none of the eigenfunctions. I hope you remember this. We do that in the second year course. Physics people must have done it in the second year course. So I assume all of you know. I'm just quickly revising. However, if the state happens to be an eigenfunction of phi I, so then of course it is very simple. So if psi is one of the phi I, then it is very simple. Just like classical mechanics, you always get AI. So there is no problem. And that is, of course, because now the psi is a specific phi. So, of course, with phi I, it is 1. With any other phi, it is 0.
Hello, sir. You are not audible.
Sir, you are not audible.
Yeah, I'm sorry I lost it. So I'll go back to the screen. Yeah, uh, I was telling, did you listen to this part? That if the psi happens to be, hello, am I audible?
Yes, sir.
Yes.
You are audible.
So did you go through the, did you hear this part? That if psi happens to be one of the eigenfunction, then you always get AI, right? And because I don't know where I lost you. So these are called the stationary states of the operator A. So one is when the state is not an eigenfunction of the operator which I'm measuring, then I get a probabilistic measurement. One in which it's an eigenfunction, I always get the same measurement. In particular, a stationary state which could be of interest is a stationary state of the Hamiltonian or energy. So I call this H psi I equal to E I psi I. So if the states which are stationary states of energy are of special importance, because energy constitutes a very important variable in natural science because of the importance of thermodynamics. So thermodynamics, of course, puts energy as a very important parameter. So most of the time we are not interested in any other operator A, but Hamiltonian for the stationary states. Of course, if a system is locked in a stationary state, we will like to find out other operators. So we know how to find that out by what is called an average value of that operator. So this is what is called the average value of A. So if I have a system in which it's a stationary state of the Hamiltonian, then my energy by the earlier measurement definition is fixed. I always get EI. But for other operators, it may not be stationary. In that case, I take the average value root. And the same thing I can do even here. When the state is not an eigenfunction of the operator A, I can actually calculate an average value here also. So similarly, average value can be calculated here as well. So usually that will be my strategy because I'm interested in energy. So I will get this and calculate the average value of the other operators, because for other operators, this may not be stationary. However, we know that if the two operators commute, that is, if A commutes with H, then of course A and H will have exactly the same eigenfunctions. So then H and A will have simultaneous eigenfunctions. In that case, it's a very beautiful thing, because I do not have not only the eigenfunction stationary state of H, but there will be also stationary state of another operator A. In which case, of course, the average value is same as the eigenvalue, right? So that's a very beautiful thing, and that is exactly what happens in group theory. Those who have already done my group theory course would remember that this was something we discussed. So in group theory, we call a symmetry operator are the operators which commute to the Hamiltonian. As simple as that, and they have these properties. So very often, in fact, there we reverse the problem. Instead of looking for the eigenstates of the Hamiltonian, we look for the eigenstate of the operator A. So one of the important symmetry operator that we discussed in group theory and has been discussed in the second year course is the parity operator, where the Hamiltonian is even and commutes to the parity operator, and we know that the parity operator eigenfunctions are either odd or even, so the Hamiltonian eigenfunctions are also odd or even. So the symmetry can be predicted. So the case in point is a harmonic oscillator, right? So in harmonic oscillator, we know that's a symmetry operator, correct? So that is a very interesting part. We'll come to one for the many electron problem very soon. So I think this is very important to realize. Then the final postulate relates to the time, that we have for any state psi. This is not a stationary state. For any state psi, the time, the psi changes with time. This is the first time we are bringing in time. So far, there is no reference to time through what is called the time-dependent Schrodinger equation. And an outcome of this is that if psi also happens to be a stationary state of Hamiltonian, right? Then this time factor, the time factor is only a phase factor. Which is basically an exponential minus IET over H cross. So something like this. Sorry. And all properties which are computed by average value or any other mean are hence time independent. That is, if this psi happens to be a stationary state. So in that sense, I said H psi equal to E psi is a stationary state of the operator Hamiltonian. But now you can see that the stationary state of energy has a further meaning. They're stationary because all properties in that state are time independent. So they don't change with time. So that's another meaning of stationarity. So you get a new meaning. All that has been coded very nicely by the Ehrenfest theorem, which says average value of any operator for any state, and that's a very general theorem. The operator can be any, state can be any. The average value is the partial derivative, or sorry, I can write it in the following manner: psi del A del T psi. So that's the psi that we have, plus 1 over H cross psi A H psi. So this is, of course, if the operator is explicitly time dependent, which is not the case for the most of the operators. So that goes off, and then you can see if the operator commutes with the Hamiltonian, the average value is time independent, which is what it should be, because it's also a stationary state of the operator A, as per our discussion before, that they have simultaneous eigenfunction. But the Ehrenfest theorem tells everything. So that's the beauty of the Ehrenfest theorem. And so basically all the time dependent parts are already there. I think all of you have done this as well. So I very quickly, I thought I will finish it in 10 minutes. It has taken a little longer than 10 minutes, but I think it's just good to still do it. With this as the introduction of quantum mechanics, we solve many problems, which are model problems. So some of the model problems that we have solved are particle in a box, right? Of different kind of box, 1D, 2D, 3D, but mainly one particle. And then similarly, harmonic oscillator, one particle, and harmonic oscillator, again, you can have a variation of 1D, 2D, 3D. We also looked at particle with a finite barrier. And discussed the problem of tunneling. Again, in physics course, those who have done probably had a larger discussion of that. And then eventually, of course, angular momentum, which is necessarily, and hydrogen atom, which is necessarily 2D and a 3D problem, hydrogen atom. Quantum mechanical treatment of hydrogen atom. And we found that the Bohr had accidentally predicted the energy correctly. The Bohr's hydrogen atom or hydrogen-like atoms. But let me just tell you that it was important that we find this out, that these are some of the problems that we did. And of course, the variations can be there and so on. We might have done even an harmonic oscillator, but all single particle problems. So most of them are exactly solvable. What was interesting was many of these problems, the solutions could have been cumbersome, but they're exactly solvable. I must also say, while solving the problem, there are 2 or 3 important properties which I could have mentioned directly in the first postulate that we use. So one of them was the continuity of the wave function. And sometimes for the barrier problems, we also use derivative continuity of psi. And then we said a single valued function. But very importantly, we said that the psi must be normalizable. So this must be finite, such that by multiplying by 1 by square root of this quantity, this can be normalizable. So that's a very important part. So some of these properties we used. In fact, we argued that because of this normalizability, we can very easily say that for harmonic oscillator, you have to have an asymptotic term, which is exponential minus some constant x squared by 2, whatever. Here, for hydrogen atom, the radial part has an exponential minus constant r, and so on. Because then it will ensure that with the finite power series, it will ensure that the psi at large value, infinite value, must be 0. So one of the points that we discussed very elaborately is that for a one-dimensional problem, let's say Cartesian coordinates, minus infinity to plus infinity, to ensure this happens, not only psi must be finite everywhere, but psi must go to 0, or the limit goes to 0, as x goes to plus infinity or minus infinity. That was very important. In a spherical polar coordinate, the radial part r always goes from 0 to infinity. So 1 infinity was good enough. To ensure this for harmonic oscillator, we use x squared, exponential minus x squared. For hydrogen atom, we use exponential minus r. However, if you remember, this was just an initial part of the solution. We multiplied this by power series to solve the second order differential equation. And we also said that the power series must truncate for the same thing to go to finite. And that truncation, which power we truncate, brought in quantum numbers. It is very important to understand how the quantum numbers came. So that is how the energy becomes quantized. For the particle in a box, of course, you did not have to do this, because with the infinite barrier, it was anyway 0 outside the box. So, but then the additional problem came that the potential had a discontinuity. So I had to ensure that the psi is continuous. So in that case, continuity of psi was used. And that led to quantum numbers. So I think very generally you must understand the origin of the quantum numbers actually lay in the goodness of this wave function. So this is very important to understand, that this is how the quantum numbers came. All right. I think with this, I will go to the parts which are the new parts of this course. But let me pause for a moment and ask any question that you have. I have very quickly given executive summary of whatever I have done, whatever we have done before, and what the quantum mechanics is all about. And what we are going to do now is what I'm going to place today and end the class today. Because it's just the beginning, first day. So I don't want to start something very new. So let me ask you any question at this stage, if any of you have any question. I mean, all this you have done
Sir,
before. Yes.
sir, is there any probability limit where non-stationary state transforms into stationary state? Like, is it when psi integration of probability of finding AI is equal to 1 with
Yeah, of course it can
psi I
transform. It
of,
can transform. Yeah, if the psi changes, it can, from a non-stationary state, if psi keeps on changing for due to certain reasons, it can become a stationary state of some that particular operator. But the wave function has to change.
sir?
Yeah.
Yes, sir. Sir,
So
also for stationary state, as it commutes with Hamiltonian, so it is time independent, and as
no,
for
1 minute.
initial,
Stationary state. 1 minute.
yes, sir.
Stationary state does not commute to the Hamiltonian. State is a function. Hamiltonian is an operator. So let us be very particular. For a stationary state, the time factor is a phase factor. There are other operators which
Okay,
commute
sir.
to the Hamiltonian. So this state also happens to be a stationary state of that operator. Okay, with the average value of that
Yes,
operator.
sir.
So nothing will change in time. So now what is your question? So
Sir,
on the other hand, if I give some
I was
perturbation,
trying to know if,
yeah, what is your
sir,
question?
if normalization is done at say t is equal to 0, will it always remain normalized? I
Well,
mean,
if it is a
is it
stationary,
true for
yeah, if it is a stationary,
non-stationary state?
yeah, if it is stationary state, yes. If it is a stationary
And for
state, yes.
non-stationary,
Yeah, non-stationary state, of course, it will depend on how it is changing with time. So we have to ensure at all time. But for stationary state, because it is mod psi square, so it is psi star psi, so time part will again cancel. So if I am normalized, with only with time, the normalization will not change. So the normalization constant is also time independent for a stationary state. But for a non-stationary state, it will of course have time. So you can
okay, sir.
normalize at a particular time, at any particular time, and you can look at how the norm changes. So those are more advanced questions. Let me tell you, when we come to quantum chemistry, we will discuss time, but because of spectroscopy, because we actually would give external field, time-dependent external field, which will actually induce transition. So we'll discuss time, but for the most part of the course, we will not worry about time. It will be a time independent problem. The Hamiltonian is time independent. So the most part of the course. So is there any other question before I come to that? Okay, if not, for most part of the course, we will answer how to solve this. So we have decided that our quantum chemistry, the problem is to solve this, get the stationary states. However, we will see it is easier said than done. So for all single particle problems, and this is where the course will begin, single particle problems, we have seen that this solution, the A psi equal to E psi, it's an exactly solvable in most cases that we have actually solved, or you can solve with some mathematical techniques. On the other hand, when we come to many particle problems, many electron problems in particular, the A psi equal to E psi is not exactly solvable. And that is the crux of the entire course. And this is something that you should not think it's only a technical matter. So it's true that for many physicists, it becomes a technical matter. And I will actually say this a little bit of a provocative statement. They can say, okay, it is not exactly solvable, but I can approximately solve and be done with that. Unfortunately, it is not okay, because in chemistry, we always deal with, and this is, I think there's a little difference from quantum chemistry and quantum physics. We always deals with difference of energies. And I must say this in the beginning, we'll come back to this discussion later. Difference of energies of two large energies. Okay, so states which have large energies, it means where the difference itself is very small. So I hope you understand the difference is very small, but difference is coming from difference of two large numbers. So if there is a small error in those two large energies, the difference will become meaningless. So all of chemistry, and I would make a very provocative statement, all of chemistry deals with the difference of energies, not the energy per se. Think of it now. Binding energy, hydrogen bond, any interaction energy, right? Chemical bond formation, right? Chemistry itself, spectroscopy, photoionization, electron attachment, excitation energy, anything that you can think of is actually difference of two energies. Even when you look at optimization of geometry, where this is a stable state, it's also a difference of energies at two different geometries. So everything that the chemistry deals with is a difference of energies. Hence, solving this accurately is very, very important. So simple approximate solutions, a hand-waving, reasonable solution is not good enough. So the emphasis has been to solve this problem. And you will see that it is fairly complex to get to the numbers which are acceptable. Today we are looking at numbers which are called chemical accuracy, of the order of 1 or 2 kilocalorie per mole, error bar. To achieve that error bar of 1 or 2 kilocalorie per mole, it's extremely difficult. It's often people go to 1 or 2 kilojoules per mole, not even kilocalorie. So I think they are very, very difficult problems is what we deal with. I should also say that for most of the course, we will use the Born-Oppenheimer approximation. I should say this, that the Hamiltonian will be defined under the Born-Oppenheimer approximation. So under that approximation, what we will do is to solve only the electronic part in a fixed nuclei. So nuclei will actually remain fixed. Though we will also tell you what happens in the nuclei move, how things will change. But for most of the course, the electronic part will be solved for a fixed nuclei. So we will talk only of the Born-Oppenheimer approximation. So I'm just giving, kind of paraphrasing what is going to come, and then we will solve. We will see how to solve. We cannot solve exactly, but we'll see how to solve. We will also first start with, on the very next class, when is there a situation when A psi equal to T psi for, in general, at least model many particle problems. Is exactly solvable. Under what condition? So here we will not talk of atoms and molecules, but under what condition they're exactly solvable, and that will lead me to what is known as the non-interacting theorem. So I will start from there, that if there is no interaction between the particles, then it is exactly solvable. However, we will then say that for atoms and molecules, that is not the case. So although this theorem is useful, knowing this is useful, we can't per se apply it, but this knowledge is something that we are going to apply as we go forward, and in particular in a Hartree-Fock theory, and that will be the basic approximation through which we'll start. So the fundamental approximation will be the Hartree-Fock theory, but a lot of groundwork has to be done. What will be the nature of psi, determinantal nature, and all that? Much of it you have already been exposed to some extent, but I think we'll go in a very systematic manner, okay, from the next class. So I will first start with the Born-Oppenheimer approximation very quickly, and allude to this when a model many particle problem is exactly solvable. And this is very important for me to say, because this phrase will come many times. And then we will see why we are not able to solve for our actual atomic and molecular problem. And then what do you do? So to do that, I need a lot of backgrounds. And one of the backgrounds is what we discussed, approximations of quantum mechanics, variation and perturbation. So I will see at what point I'm going to bring them. Everything will not be brought exactly in the way the syllabus is, but they will all come at different times, okay? So I think we will stop here today. See, today's class was just an introduction to the course, and I think we will start from there. However, the recording will be made available. Sangita, the recording is automatically going?
Yes, it will automatically go to the Google Drive, and I will put the link on Wheeler.
Yeah, so they can download directly. So I don't have to send the recording.
No, you don't have to send.
Okay, so I will only share the slides in the Wheeler. All right, so I will
Yes.
only share the
And,
slides. Yeah.
Yeah, if you like, then I can create a YouTube channel also for this course and upload all the things on YouTube.
The only problem with the YouTube channel is that I have found that to conversion to even the standard SD mode takes such a huge time and space that I don't know if you don't have access to YouTube Premium, whether you can do that. Have you ever done it?
I did it for the last course. It takes some time, yes, but I can manage to do it.
Okay, that will be fine actually. Because I tried, it was taking too much time, so I lost patience.
Right, it takes quite some time.
Yeah, okay, all right. So yeah, fine, that's okay. But the recording will be anyway made available to them.
Yeah.
All right. So I think
Recording is anyhow, it will be available soon.
Let me also tell the class timings now. Now that today we have a Monday, so next class is Thursday, right?
Yes, Thursday 9 a.m. is next
9
class.
to 10 a.m. This is something to be discussed, and then Friday 10 to 12 a.m. and 10 to 12. So this time we will not only have class, but also as the academic section 1, it will be basically a tutorial section. But then we may not use all of 2 hours for tutorial. So we'll split into class and discussion, because otherwise your class timing will be only 2 hours. You have to move the class, but it doesn't matter. We can, during this also, we can move it forward. But I don't like to take the class rapidly and discuss everything here. So I will probably move a part of it in the class, part of it tutorial and discussion. Is that okay, all the students? Hello? Hello?
Yes, sir.
Yeah, that's
Sir,
okay, right? So,
Sir, actually, some DPS people have clash on Monday's class, today's.
but how come this has happened? I mean, this academic section has to be flagged, no? Because if I now change the Monday's class, some others will have a problem.
Yes, sir, I think that will not be the case, because the other course is atomic physics, which is instructed by ON manager Nirmal Ghosh, and they themselves have problem with the timetable. So they will shift. I think they will shift the this
Okay,
timing.
that's good. So that's good. So today they are not taking the class, right?
Yes, sir.
So let us. So Sangita, just please be in touch with them. Sangita?
Yeah, sure. Also, one request, like last time also, if you can make a WhatsApp group of all of you, then that becomes easy for us to
much
communicate.
easier, yeah. So if the 2 more people join, then we put all together WhatsApp group. So what they're essentially saying that the physics people have a class on 10 to 11 as of now, but even the physics faculty himself has a problem with this time on Monday. So they may automatically change in a natural course. So then their problem will vanish. But if they continue to take, if they continue to take,
things are not happen, then we have a backup plan of free time, then we can
We'll
discuss it
see.
later.
Yeah, we'll see. If
Yes.
it doesn't happen, Sangita, then two of them who are doing physics will miss this class or have a class. So we may have to shift this Monday's time. Okay?
Yeah, then you can do the proper class on Friday, and then maybe Monday can be more tutorial. If
Sir, actually, this is not a problem with two of us. This is a problem for another student who is not attending this class now. He is
What is
attending.
this?
He is Subhrangshu Vishwas,
Okay.
and he is attending that class
okay, so
so that he can confirm that the shifting is time is happening or not.
So
In that,
today that class is taking place.
yes, sir, and
Okay.
he is there to make us sure that whether the time
Yeah, okay.
shifting in that course is happening or
Fine.
not.
Yeah, I know Subhrangshu. I think he attended my group theory course also. So
Yes,
that's
sir.
fine. Yeah. So we'll see. So Sangita, be in touch with them for this timing.
yeah, sure. Just make a WhatsApp group. I will email my phone number so you can add it to the group.
We have a WhatsApp group and
Yeah.
with the students only. And if you
Yeah,
can give your phone
I
number,
think
we can
your
add you.
my number is available to you because I
Yes,
was
yes,
there in the last WhatsApp group in
yes,
group
yes,
theory course.
yes.
And Sangita
I
ma'am's
will,
number you can take.
or I
So
can
that'll be
message
no
it right
problem.
now if you can copy it
Yeah.
now.
Yeah.
I will.
Yeah.
Okay,
Okay. All right. So I will close it now, today's class, and then we'll meet again on Thursday at 9 o'clock. Okay. All right. Okay. Thank you. So let me stop sharing the screen. And yeah, thank you very much. Okay.